In this section, our goal is to rigorize what we ended the last section with, namely, I took a system of equations, did some math, and ended up with some kind of matrix that Lord only knows why we'd care. So, to rigorize all that, we're going to need row reduction and so-called echelon forms. Now, row reduction goes back to the end of section 1.1 where I talked about elementary row operations. Now, if you remember what those were, I can swap two rows, I can multiply a row by a constant, or I can take row I, multiply it by alpha, and add to row j, and leave it there. With these three alone, we can end up with something we're going to call an echelon form. So, okay, why do I have echelon forms right there? Whatever. Anyways, in a non-zero row, the leftmost non-zero entry is called a leading entry. Okay, so let's grab some matrix here. Let's see, we have 0, 1, 2, 3, 1, 2, 1, 0, 0, 0, 1, 4. Okay. In a non-zero row, all three of these are non-zero rows. The leftmost non-zero entry is the leading entry. So in the first row, that's the leading entry. In the second row, that is the leading entry. And in the third row, that is the leading entry. Now, we want these leading entries to be situated in a very particular way. Now, thinking back to the last section, what I ended up with was an augmented matrix that looked like that, and then I had three numbers there. I don't recall what they were. Now, think about this. This one, and that one, they're all leading entries. And from this, I was able to discern that this variable, namely x1, if I'm thinking of it, was that value, x2 was that, and x3 was that. So from this particular form on the left of my augmented matrix, I was able to infer very easily things about my actual system. Let's make this a little more rigorous. A rectangular matrix is in row echelon form, REF, if we have any zero rows, they're all on the bottom. So 2, 3, 1, 5, mess. All of my zero rows have to be situated along the bottom of this matrix. Okay. The next step is we must have all leading entries stair-stepping down. This is the one that's the hardest to explain but the easiest to see. My leading entries here, they stair-step down. Here, my leading entries do not stair-step down. They zigzag all over the place. That is not what we want. Now to give you another example, we have 1, 2, 3, 0, 0, 1. 0, 0, 0, and let's say 1, 2, 3. Look at that augmented matrix. All of our, that's gotta be a 0. My 0 rows on the bottom, and my leading entries are still stair-stepping down, okay? And then the next criterion is the leading entries must have zeros beneath them. Well, leading entry, all zeros. Leading entry, all zeros. Leading entry, assuming those are all zeros, then yes, that's all good. Now, if each leading entry is a 1, and it's the only one in its column, we say the matrix is in reduced row echelon form. So this matrix right here in particular is in reduced row echelon form because we satisfied these first three, and each of my leading entries is actually a 1. If I change this ever so slightly to 2, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, 4, and let's actually put a 0 row in there for good measure. this is not in reduced row echelon form, but it is in row echelon form. What does this need to be in reduced row echelon form? This entry right here, the leading entry, needs to be a 1. All right, let's do some examples of echelon forms. All right, 2, 3, 4, 1, 1, 2, 0, 0, 0. Is that in echelon form? To see whether or not this is in echelon form, let's go through the checklist. Are all the 0 rows in the bottom? Yep. Do the leading entries stair step down? Well, remember, the leading entry in a given row is the first non-zero entry. So that's a leading entry, and that should be a leading entry. Do they stair step down? No, they don't. So this is not in row echelon form. All right. Let's say, well, I don't want to draw an arrow there. Let's just give another example. Let's say I had 2, 3, 4, 0, 2, 2, 0, 0, 0. Is this in row echelon form? All right. Lane entries, we identify those. Do they stair step down? Well, they certainly do. And they only have zeros beneath the lane entries. Well, yes. So this is in row echelon form. The next question to ask is it in reduced row echelon form? Well, no. No, it's not. Because the lane entry, first off, needs to be a 1. Well, neither of these lane entries is a 1. So it's row echelon form, but not reduced row echelon form. All right, well, let's change that one ever so slightly so that the leading entries are 1s. All right. We know this is row echelon form. Check. It's reduced row echelon form. Well, it is not, because if you think back, the leading entry needs to be a 1, but not only that, it must be the only one in its column. Oops, how did I get a 0? There. There's a 3 right there. So this is still not reduced row echelon form, because that needs to be a 0. All right, let's write this one down. 1, 0, 4, 0, 1, 2, 0, 0, 0. We know this is row echelon form. Is it reduced row echelon form? Well, yes, it finally is, because the leading entries, both 1s, are the only ones in their respective columns. All right, let me turn this on its head ever so slightly. 1, 0, 4, 0, 1, 2, 0, 0, 1. Is that reduced row echelon form? Well, let's go through the checklist. Leading entries, first non-zero entry in each row. Do they stair step down? Yeah. Are leading entries the only zeros in that row? Well, no. So this would need to be a 0, and that would need to be a 0. So this is not reduced row echelon form. To make it reduced row echelon form, these would need to be zeros. So that would need to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Now that is reduced row echelon form. And we're going to learn that corresponds to something that is undesirable. Now, one thing I probably haven't made as clear as I need to is this. We're given some matrix A. And we're going to view it as an augmented matrix. by a series of row operations, namely those elementary operations, we are going to reduce this matrix A into a new form, A prime, where A prime is the reduced row echelon form of A. This whole process here is called row reduction. It is from the reduced row echelon form, something that looks like this, or like this, that we can pinpoint what the actual solutions to our system will be. Now, we have a theorem that states that every matrix, no matter what matrix I give you, its row equivalent to only one reduced echelon form. So, in other words, given a matrix A, I do row operations on it until I get the reduced row echelon form of A. Well, this thing appears on the right here is saying that there's only one form of this. Well, thinking back to one of the most important questions in mathematics, that is saying that the reduced row echelon form of a matrix is unique. And even more to one, so it's saying that there exists. So this is an existence and uniqueness theorem for us. It says that given a matrix A, its reduced row echelon form exists and is unique. And that shouldn't be too surprising, because if I perform these row operations until I get where I need to get, namely the reduced row echelon form, there won't be hiccups along the way that will get rid of uniqueness in a sense. You know, every function is injective or one-to-one. All right. Definition. A pivot position in a matrix is a location that corresponds to a leading one in its reduced row echelon form or row echelon form. A pivot column is a column that contains a pivot position. All right. These leading entries, so like 1, 0, 2, 0, 1, 0, 0, 0, 0, 1, 2, 0. This and this, these are pivot entries, and these are the pivot columns. You'll find that some books will use the word pivot interchangeably with a pivot position or a leading one. So be mindful of that. Pivot is essentially the same thing as a leading entry. People use them synonymously. Okay. I have a rather gruesome matrix here. I want to completely row reduce it, and then afterwards identify the pivots and pivot columns of the original matrix. All right, let's get started on this beast. Now, thinking back to the criteria for reduced row echelon form, the first thing is we need our pivots, our leading ones, to stair step down. So this entry right here needs to be a 1. Well, what I'm going to do is interchange rows 1 and 4. To interchange rows 1 and 4, what I will do is the row operation P14. My goodness, how'd that happen so quickly? Oh, I paused it. I will spare you all the writing of all these numbers because it will drive you mad otherwise. And speaking of driving you mad, I suppose now is the time to give you a fair warning. Our entire course is going to be comprised of doing these row operations on these matrices. Mistakes are inevitable. And I mean inevitable. So, bear with it all. Okay. We have our lean entry. We're going to use this lean entry to eliminate the two entries beneath it. Because if you think back, a pivot position needs to have zeros above and below it. So to do this, I will use row 1 and add to row 2. So that's E12 of 1. And then I'll do 2 times row 1 plus row 3. So that's E13 of 2. I'll pause it now and do this operation for you. Now in this result, look at rows 2 and 3. They both carry a multiple of 2 and 5 respectively. So what I'm going to do is multiply row 2 by 1/2 and row 3 by 1/5. Why am I going to do that? Well, in the next step in our row reduction, you'll see why. So take row 2, hit it with a 1/2, take row 3, hit it with a 1/5. Well, looky there. Rows 2 and 3 are identical. Well, what that means I can do is I can use row 2 here to eliminate row 3 completely. So namely, E23 of -1. I will take -1 times row 2 and add to row 3, thereby eliminating row 3. Turn it into the 0 row, basically. But you know, while I'm at it, why don't I use this leading entry to destroy that 4 and that -3? That's called efficiency. So to do that, I will do E21 of -4. So that's taking -4 times row 2 and adding it to row 1, thereby eliminating that 4, turn it into a 0. And then I'll do 3 times row 2 plus row 4 to get rid of that -3. So that's E24 of 3. All right. What I have now is something very close to echelon form. This -5 here needs to be a 0, or a 1 rather. So what I'm going to do is multiply row 4 by a -1/5. And while I'm at it, swap rows 3 and 4. Let's pause here. Is this in row echelon form? All right, let's identify our leading entries. Boom, boom, boom. Are all of our 0 rows on the bottom? Yep, check. Do our leading entries stair-step down? Yes, check. Do our leading entries have only 0s beneath them? Yes, check. So therefore, this is indeed in row echelon form. Well, is it in reduced row echelon form? No, it's not, because the leading entries, although they are all 1s, that's one good step, we need 0s both beneath and above them. Well, the first 2 columns are all good. It is the 4th column that is problematic, because both of these 3 and -3 need to be 0s. So let's do that really quick so that this will actually end up being in reduced row echelon form. All right, so we're going to use row 3 to eliminate this entry in row 1. So we will do row 3 to row 1, and we're going to use a -3 there. And then we're going to use row 3 and row 2, and we'll use a +3 on that one. Well, looky there. We got the 0s above that position like we needed to. Now, hopefully you were doing these computations alongside me, and you realize that using this row to eliminate the entries above it was really nice because of all these 0s here, and, well, there's a 0 here, but ignore that fact. These 0s here, we know that they will not, therefore, influence those entries when we do the row operations to eliminate those. That is why we actually carry out this process in the exact manner in which I did it. Let's go, oh, good Lord, that was a lot. Let's go back to the beginning and just kind of recap. I first put a 1 there. I use that to eliminate the entries beneath it. I then identified that position, and then I noticed that once that was a 1, when I added it onto the rows above and below it, that 0 there preceding it meant that I didn't have to change anything in those front rows either. And that pattern carried through the rest of the problem. So by stair-stepping down whenever possible with our lean entries, we can really eliminate a lot of the work in the process of doing this. Because surely you've seen now that took over 7 minutes. This is tedious business. Again, trying to turn something that's extremely abstract, namely all these row operations, back into the linear equation form, let's look at the next slide. In this example, I ask you to consider the reduced or echelon form of this matrix. We need to view this as an augmented matrix, so it came from some kind of system of linear equations. Let's turn it back into equation form. All right, so the first row, we're going to think of these as x1, x2, and x3 for the columns. This translates back into x1 plus 2x3 equals 3, x2 plus 5x3 equals 7, and then this last row is saying x3 is free. All right, so turn it back into an equation, and let's solve it now for the pivots. So that's x1 equals negative 2x3 plus 3, x2 equals negative 5x3 plus 7, and then to turn this into an equation, x3 being free is equivalent to us as saying, if you think about it, x3 equals x3. All right. Now, the pivot variables, namely these 1s, which were these right here, the 1 and the 2, those are called the basic variables. They're very basic, nothing extra about them. And the remaining variables, namely this x3, that's a free variable. Now, we could have identified that from the very beginning. This is the x1 column, that's the x2 column, and that's the x3 column. This column has a pivot. Therefore, there will be a basic variable for x1. x2 has a pivot. Therefore, it'll be a basic variable. x3 did not have a pivot in the necessary pivot position. Therefore, it'll end up being a free variable. Now, thinking what this all means, there's a dependence relation between x1, x2, and x3. Since x3 is free, it can be any value of x we desire. So I could take x3 to be, say, pi. Well, if x3 is pi, then x2 is then forced to be negative 5 pi plus 7, and x1 is forced to be negative 2 pi plus 3. Well, how many solutions will this matrix equation have? Or namely this system? Well, infinitely many. There's just one solution for every choice of x3. All right, let's employ this with an actual example. Here I have a simply marvelous augmented matrix. And what I want to do is determine its reduced echelon form. And from that reduced echelon form, determine all the basic and free variables and say whether or not the solution is going to be unique. Well, thinking about it, if I have free variables, is that solution going to be unique? Well, no, because a free variable gives us a relation among the other variables and therefore infinitely many solutions, assuming, of course, that the system is consistent. So let us quickly, and I mean quickly, row reduce this thing. All right, the very first step we want to do is use this one to eliminate both of those entries. So what we need to do is 2 times row 1 plus row 2. That's E12 of 2, and then E13 of negative 3. Now this is what we end up with, and in the process of doing this, I realized I must have made a mistake or didn't really have the matrix I wanted in here. So what we're going to do is a little thing I like to call change the original problem to make it match what I wanted to do. So let's see here, because you see what's happening here is when I add these 2 rows up, I'll end up with a 0 and a 1 there. That'll make this thing inconsistent. I want this thing to be consistent. So what I will do is notice that that entry right there, say, needs to be the exact opposite of what that row is. So it needs to be a negative 3. So that needs to be a negative 3, so that meant that one needs to be a negative 3, noticing that there's a 0. So that's how I came up with that. All right. Now, in my next step of my magic trick of this changing the problem, I'll add rows 2 and 3. So that's E23 of 1. Okay, we have our 0 row here. Our lean entry for this row is there. That needs to be a 1. So we hit this row with a 1/3. And while I'm doing it, I will say, all right, row 2 plus row 1, notice that will be a 1, store to row 1. So what we'll have is E2 1/3, and then E21 of 1. Notice that this step must precede that one, or for this to even make sense, because I'm acting on the same row. So what we have now is indeed the reduced row echelon form. What I observe is pivot, pivot, x1, x2, x3, x4. So I have for my basic variables, sorry, it might help you remind you what the problem was. We're supposed to determine the basic and free variables. The basic variables are x1 and x3, and the free variables are x2 and x4. And we see that because there's no pivot entry in the x2 and x4 columns. Now next up is the solution to this system unique. Well, no, it's not, because we have a consistent system with free variables. So there will be infinitely many solutions to this particular system. Now, to sum all this up, we have a theorem, and it's a wordy one. So the first part says, a linear system is consistent if and only if the rightmost column is not a pivot column. Okay, so let's say we have some kind of reduced echelon form like that. Think what this is saying. That's the x1 column, x2, and x3. x1 and x2 will both be free variables. There's no pivot there. This says then that x3 equals 2. That's what this row is really saying. And this last row is saying that 0x1 plus 0x2 plus 0x3, namely 0, equals 1. This pivot is showing us that we have 0 equals 1. And so that's why the rightmost column cannot be a pivot column in order for the system to be consistent. So this first part of the theorem is just common sense applied to our interpretation. Now, in the case that our system is consistent, namely the rightmost column is not a pivot column, it has a unique solution in no variables, or it has infinitely many solutions and at least one free variable. This is a fact I was using during my discussion the entire time. Infinite many solutions corresponds to a free variable, and no free variables corresponds to a unique solution. And this is just finalizing that exact statement.